Hi everyone, this is Sina, and today we're going to talk about high RPM flow requirements. In this picture, we have a typical naturally aspirated engine power and torque graph. As you can see, at higher RPMs, uh, we have a decrease in both torque and power. We're going to evaluate why this happens, what are the reasons, and how to mitigate them, or even also increase the engine torque and power at these RPM range. So, what is the core problem? The core problem is uh, this phenomenon happened because of decreased volumetric efficiency at higher engine speeds. There are also some other factors like increased engine friction, but the main reason is decreased volumetric efficiency at those RPMs. And when volumetric efficiency decreases, you get lower air inside a cylinder, thus lower fuel can combust and lower energy released, and because of that, lower torque and power. Uh, I have created a list here, the main reasons why this happened. The first one being higher flow velocity. So when the RPM goes up, actually the flow velocity also goes up and actually it scales with the RPM. So at higher RPMs, we have higher flow velocity. This means higher frictional losses. And this translates into more pressure drop. So when you have more pressure drop throughout the system, you get lower volumetric efficiency and hence power and torque. The second reason being choke flow at intake valves. Again, as RPM goes up, the flow velocity goes up, and during the first parts of the intake lift, because the cross-section area is small, the flow velocity increases and it reaches sonic level, reaches around Mach 1, and when you get that would be a choked flow. Uh, so at higher RPMs, we have more choking at the intake valve events. Because of that, volumetric efficiency drops. This third one would be poor pulsation utilization. We have another phenomenon called pulsation. When intake or exhaust valves open, there would be some pressure pulsation going through the intake system. And when they reach some points in the intake system, like in abrupt cross-section increase, they will reflect back and come back to the engine. Uh, so if you tune properly the cam duration and valve timing effects, you can utilize these pulsations and increase the volumetric efficiency. Uh, this heavily depends on the intake system geometry and valve timings and durations. Uh, so you can fine tune them for different RPM ranges. When you fine tune them for mid-range RPM, you get a decrease in volumetric efficiency for higher RPM ranges. So you can actually fine tune them for higher RPMs to use that potential to increase the volumetric efficiency at those RPMs. The fourth one being higher exhaust pressure. So as the RPM goes up, it means that at the same amount of time, you're actually pushing more flow and mass through the exhaust system. So because of that, the exhaust pressure goes up and you get much more exhaust back pressure. So if you can somehow uh, decrease that exhaust back pressure at higher RPMs, you get much more volumetric efficiency, and hence power and torque. The last one would be poor ramametric utilization, just like pulsation. This would be a phenomena that can be used to increase volumetric efficiency at higher RPMs. So when the piston, uh, so just like uh, the intake valve closes during the compression stroke. At some time after compression stroke, like 50 degrees after the bottom dead center, the intake valve closes. At higher RPMs, the incoming air has a lot of velocity, and because of that, it has a lot of momentum. So when the piston goes up, uh, the air momentum it can actually resist the piston moving upward. So if you choose the intake valve close timing properly, you can actually utilize this and closing the intake valve in a latter phase, but results into higher volumetric efficiency and higher, much more air being inside the cylinder. And because of that, you can get more torque and power. So what is the solution? The solutions are pretty straightforward. Like there's a trend, and we know what is the trend. For example, for higher flow velocity, which results into higher frictional losses, you can actually use shorter pipe lengths and increased pipe diameter. Or for choke flow, you can use higher valve durations and proper timings plus larger valve diameters. Okay, the third one, which was poor pulsation utilization, you can use correct pipe lengths and diameter for the desired RPM range. And for higher exhaust pressure, you can use larger pipe diameter inside the exhaust system. And for poor ram effect utilization, you can use correct intake valve close timings. But is it that simple? Of course not. It will not be that simple. As I said, we know the trends. We know we can use shorter pipe lengths or increased diameters or higher durations, but the answer would be how much? What are the correct values for these attributes if you want to increase the volumetric efficiency for example, 6 to 7,000 RPM or 8 to 9,000 RPMs? These values would be different. So it is important to know what are these values, not the trend. So for the pulsation tuning, this is a very complex subject. For us to be able to find the correct values, it requires at least 1D simulation packages or extensive and expensive prototyping, or you'll have a huge amount of experience and have access to a lot of similar data. What does this mean? It means if you don't have the amount of budget and time for use prototyping, you have to use at least one-dimensional simulations. Even this would not be that easy because that simulation model shall be able to correctly replicate your engine behavior. So it has to be calibrated. And for its calibration, you need a lot of data and some complex data, which requires very expensive measurement devices, or you use some consultation companies for that. Or based on your experience for tuning engines, if you have been able to work on different engines, you will get you'll definitely find the best values for similar engine setups. Or you can use, or if you have access to other people's experience, you can use those data. But the most reliable way would be using simulation packages or prototyping. But the prototyping would be very expensive and time consuming and extensive. For frictional loss, that would be very simple and easy to find the best values. But actually, if you have access to 1D simulation packages, you can actually find the best values for your engine even if that model is not even related to your engine. For example, if your target engine is a four-cylinder uh, large bore engine, you can actually use a six-cylinder small bore engine model to find the best values. What you would do would be like find an increase factor diameter at different RPM range to reduce the frictional losses, and you can use that increase factor for your engine also. So this one would be very simple. The ramific tuning, this is again very simple. You can use simple dyno runs and find the best intake valve close timing for that RPM range. You want to increase its volumetric efficiency. So this one would be even simple. And choke flow, for the choke flow mitigation, just like pulsation tuning, this one would be very complex. It requires at least 1D simulation or extensive and expensive prototyping or a huge amount of experience and shared data. So this is it. As you can, as I've said, some of these tunings requires they are very complex, so they require a lot of knowledge about simulation or prototyping, or you have to have a lot of experience. But for some of them, there would be uh, some simple procedures to find the best values. You can fine tune them easily, but the main ones being pulsation and choke flow, they require uh, very complex procedures. So fine tuning them is not very simple, uh, and it requires someone with or a team with heavy knowledge about the uh, subject. So that would not be simple. Thank you guys. This is it. We'll definitely talk about pulsation and choking much more in the upcoming videos. Uh, we will evaluate in much more detail. I'll probably show you some simulation runs regarding these subjects so we can uh, get more detail and have a better understanding about them. Thank you all. Have a good day and feel free to leave your comments. I'll definitely be answering. Thank you.